Let's talk about going from Earth to Mars and whether this is feasible. And let's talk about, like, if we wanted to, say, colonize Mars, how easy would that be compared to, for example, colonizing the moon? Simplistically, you leave the Earth, you get to Mars, and you land on Mars. That's simplistically how you do it. Let's talk about all of those details now. So, leaving Earth, we've talked in the past about what escape velocity means. And we know that escape velocity for Earth is 11,200 meters per second at the surface. So, if we want to escape Earth, we need to have a rocket that is capable of giving us 11,200 meters per second delta V. Then, if we want to go from Earth to Mars, we need to use the Hohmann transfer. And in order to do that, we need a delta V where we get onto the elliptical orbit. And then we need to have a delta V where we get off of the elliptical orbit. So the on-ramping of this Hohmann transfer is about 2,943 meters per second. The off-ramp of this is 2,650 meters per second. Then if you want to land on Mars, we actually don't need to use the escape velocity of Mars because we use the atmosphere of Mars to actually aerobrake, and we can slow way down so we don't have to use jets. So let's call the delta V for landing on Mars about 1,250 meters per second. So how much delta V is needed in total? So to escape from Earth, you need 11,200. To get on the path to Mars, you need this 2,943. To stay at Mars, you need this 2,650. And to land on Mars, you need 1,250 meters per second. In total, with all of those delta V's added together, the most we've ever put on Mars is something about the size of a minivan. How does this compare to getting to the moon? We've put a lot of stuff on the moon. If we roughly escape from Earth, we land on the moon. Landing on the moon is about 2377. We escape from the moon, so we go down to the moon surface, we come off of the moon surface, and then we land on Earth, which basically we call this very small amount of delta V because we use the atmosphere, once again, of Earth to land on Earth. Now, when we've gone to the moon and back, we carried 45,000 kilograms with 3 people to the moon. To go to Mars, we've only taken 3,839 kilograms. So interestingly, it's harder to get just to Mars than it is to get to the moon and back. So we can get to Mars, but we just can't take very much mass there. If we wanted to take 45,000 kilograms to Mars, it would be very, very, very hard. And actually, we couldn't do that with the technology that we have. So what would it take to go to Mars, then get back from Mars? And if we used one rocket, what would that take? Well, if you wanted to escape from Mars, it would take 5,028 meters per second. And then basically we want to reverse our Hohmann transfer. And so we want to get on a path to go to Earth in the Hohmann transfer, which is 2,650 meters per second. Then when we want to stay at Earth, it's 2,943 meters per second. You can see that that's the reverse of getting to Mars. And then we're going to land on Earth, and it's very small because we can use the rich, robust atmosphere of Earth. So what's the problem? The problem is fuel. It takes a lot of fuel to do these delta V maneuvers. So let's go through some of this fuel. And let's compare basically sending 1 kilogram to the moon and back to 1 kilogram going to Mars and back. And a pineapple is about 1 kilogram, so it's a nice thing to use. So how much does it take? How much fuel does it take to send this pineapple to different places? So if we wanted to start at Earth, and we wanted to just go into Earth's orbit, it would take about 7.7 kilograms of fuel to launch this pineapple into low Earth orbit. If we wanted to go escape Earth's gravity, it would take about 24.3 kilograms. So we just send it off into space and just have it be away from Earth. It's around 24.3 kilograms. If we wanted to go to the moon, it would take about 46.47 kilograms. And if we wanted to go to the moon, then back to Earth, it would take about 115 kilograms of fuel, significantly more. Now, if we wanted to go to Mars, it would take 189 kilograms of fuel. All right, so it's more fuel to take 1 kilogram to Mars than it is to go to the moon and back. If we wanted to go to Mars and then back, it would take 2,886 kilograms of fuel, significantly more if we used a single rocket. But let's say that we were at Mars and we had some way of refueling. If we wanted to just go from Mars back to Earth, it would only take 14 kilograms, okay? So if we could refuel at Mars, it would be significantly easier to get back from Mars. But we can't refuel at Mars right now. We have no refueling stations. So look for that as maybe a technology that companies will be developing in the future. So what can we do right now? SpaceX's Falcon Heavy is one of the largest rockets in rotation. We've launched a bunch of Falcon Heavies. And so that would allow us to take stuff to the moon. Not get it back, but we could take stuff and we could land on the moon. So in summary, 1 kilogram to Mars is harder than 1 kilogram to the moon and back. We've sent 50,000 kilograms to the moon and we've left some stuff there. And we used the biggest rocket that we've ever created to do this 50,000 kilograms to the moon. Using our largest rockets right now, we can send about 3,000 kilograms to Mars, and that's about it. We can't send much larger things to Mars. We would need a lot more than 50,000 kilograms of equipment to sustain an astronaut. Think about it. 50,000 kilograms basically allowed us to go to the moon and back, and that took roughly a week to go to the moon, go down to the moon, do things on the moon, come back from the moon. Took roughly a week. So 3 people in a little car-shaped object, basically, for about a week, not too horrible. But if you were to shove some astronauts into something and expect them to survive for 8 months, you would need something significantly larger than that for an 8-month mission. You'd also need a lot more food, a lot more water, etc. And that's just to get to Mars. And so we need a much, much, much larger rocket. 8 months is only to get to Mars. So getting to Mars is actually very, very hard and very, very expensive, let alone getting back from Mars, which is impossible at this point.